This lecture discusses statistical inference for two population means using independent samples when population standard deviations are not assumed equal. Draw independent simple random samples from two populations. Let the sample size be n1 and n2, and the sample means x1 bar and x2 bar. Recall that we have discussed the sampling distribution of the difference of sample means x1 bar minus x2 bar. Its mean is mu1 minus mu2, and its standard deviation is given on the slide. Let's consider the z-score of the difference of means. It is x1 bar minus x2 bar, subtract the difference of mu's, and then divide it by the standard deviation of x1 bar minus x2 bar. In the previous section, we have assumed that the population standard deviations are equal and discussed how to test hypotheses and construct confidence intervals. In some applications, the population standard deviations are not equal. We will discuss this scenario in this lecture. Because population standard deviations sigma 1 and sigma 2 are unknown, we replace them by the corresponding sample standard deviations S1 and S2. In order to conduct statistical inference, we need to know the sampling distribution. The first displayed expression is obtained by replacing sigma 1 and sigma 2 in the z-score in the previous slide by the sample standard deviation S1 and S2. Here, we need to assume that X is normally distributed. Additionally, we assume that there are independent samples of size N1 and N2 from the two populations. Then this T has approximately a T distribution. The number of degrees of freedom can be calculated from the data. We use the symbol delta to denote the number of degrees of freedom. The expression of delta is complicated. It mainly depends on the sample standard deviation S1 and S2 and the sample sizes N1 and N2. First, I want to emphasize that the variable t only approximately follows a t distribution. Notice that in the previous lecture on equal standard deviation, the distribution is exactly a t distribution. Next, delta can be a decimal. For practical usage, we need to round it down to the nearest integer. By rounding down, I mean dropping the fractional parts. It is not rounding. For example, the value 10.7 will be rounded down to 10, and the value 9.2 will be rounded down to 9. Till now, probably you will understand why we prefer the scenario with equal standard deviations. For scenarios with equal standard deviations, the calculation will be much easier. This slide lists the steps for non-pooled t-test. The assumptions include simple random sample, independent samples, and normal populations or large samples. The assumptions are similar to those for pooled t-test. The only difference is that the assumption of equal standard deviation is dropped. We first need to identify the non and alternative hypothesis. The non-hypothesis is mu1 equals mu2. There are three possible alternative hypotheses, namely two-tailed test, mu1 not equal to mu2, left-tailed test, mu1 less than mu2, and a right-tailed test, mu1 larger than mu2. We also need to decide on the significance level alpha. In most applications, alpha equals 0.05. Occasionally, alpha equals 0.1 or 0.01. We then compute the test statistic. T0 equals the difference of sample means divided by the standard deviations of x1 bar minus x2 bar, with sigma replaced by the sample standard deviation S1 and S2. We can continue with the critical value approach or t-value approach. When using the critical value approach, the choice of critical values depends on the type of alternative hypothesis. For two-tailed tests, there are two critical values, plus minus T alpha over 2. The rejection region is less than negative T alpha over 2 or larger than T alpha over 2. For left-tailed test, the critical value is negative T alpha. The rejection region is less than negative T alpha. For right-tailed test, the critical value is T alpha. The rejection region is larger than T alpha. Make sure to calculate the number of degrees of freedom correctly. It is delta rounded down to the nearest integer. If the test statistic falls in the rejection region, reject H none. Otherwise, we do not reject H none. When using the p-value approach, we also need to calculate the number of degrees of freedom. It is delta rounded down to the nearest integer. For two-tailed tests, the p-value is the sum of probabilities of less than negative absolute value of t0 or larger than absolute value of t0. For left-tailed tests, the p-value is less than t0. For right-tailed test, the p-value is larger than t0. If the p-value is less than significance level alpha, we reject H none. Otherwise, we do not reject H none. Last, make sure to interpret the results of the hypothesis test. Let's look at one example. Several neurosurgeons wanted to determine whether a dynamic system reduced the operative time relative to a static system. The sample contains 14 cases for the dynamic system and 6 cases for the static system. Comparing the two box plots, we can see that the length of the box for dynamic is much longer than that for static. It indicates the inequality of standard deviations. We mentioned before that the length of the box in a box plot equals interquartile range. Although it is not standard deviation, unequal interquartile range usually suggests unequal standard deviations. The observation is also confirmed by the numbers. The sample standard deviations are 84.7 and 38.2. They are clearly unequal, which suggests that the population standard deviations are not equal. This tells us that we cannot use the pooled t-test. We can only use the non-pooled t-test. The two normal probability plots show mild deviation from normality. And there are no outliers. We can apply the non-pooled t-test. The null hypothesis is mu1 equals mu2, where mu1 is the mean dynamic time and mu2 is the mean static time. Because we want to know whether a dynamic system reduced the operative time, the word reduce suggested a left-tailed test. Therefore, the alternative hypothesis is mu1 less than mu2. Let's solve the problem at significance level 0.05. The test statistic is computed as follows. The value t0 equals x1 bar minus x2 bar divided by the square root of s1 squared divided by n1 plus s2 squared divided by n2. We have already calculated the sample mean and the sample standard deviations in the previous slide. Plug in all the numbers and do the math. The test statistic is negative 2.681. Next, we need to calculate the number of degrees of freedoms. When you plug in the numbers, make sure to do it correctly. In the numerator, the square is outside of the bracket, or we do addition first and then square. However, in the denominator, we do square first and then addition. Do the math and you will get 17.83. The number of degrees of freedom is 17. Notice that we need to round 17.83 down to the nearest integer, which means dropping the fractional part, no matter how large or small it is. This is a left-tailed test with significance level 0.05 and 17 degrees of freedom. When using the critical value approach, the critical value is negative T alpha equals negative T.05. The value is negative 1.74. The test statistic is negative 2.681, which is smaller than the critical value. The test statistic falls in the rejection region. Therefore, we reject H0. When using the t-value approach, we can calculate the t-value using Excel. It is t-dist negative 2.681, 17, true. The p-value is very small. It is 0.00789. The p-value is less than the significance level. Therefore, we reject H0. Both approaches lead to the rejection of H0. At the 5% confidence level, the data provide sufficient evidence to conclude that the mean operative time is less with the dynamic system than with the static system. We can also construct a confidence interval for the difference of means. This procedure is called the non-pooled t-interval procedure. We have the same assumptions as non-pooled t-test, which include simple random sample, independent samples, normal population, or large samples. To find a confidence interval for the difference of means, we first need to find T alpha over 2 with delta degrees of freedom. The endpoints of the confidence intervals are x1 bar minus x2 bar plus minus T alpha over 2 times the square root of s1 squared over n1 plus s2 squared over n2. Notice that the confidence interval still follows the general form of point estimate plus minus margin of error. Last, make sure to interpret the confidence interval. Let's obtain a 90% confidence interval for the difference between the mean operative times of the dynamic and the static system. Notice that here alpha equals 0.1. Therefore, T alpha over 2 equals 0.05 equals 1.74. Here we use 17 degrees of freedom. We have calculated the value of delta in the previous example. The 90% confidence interval is therefore 394.6 minus 468.3 plus minus 1.74 times square root of 84.7 squared over 14 plus 38.2 squared over 6. The 90% confidence interval is therefore negative 73.7 plus minus 47.8. We can be 90% confident that the dynamic system relative to the static system reduces the mean operative time by somewhere between 25.9 minutes and 121.5 minutes. We have discussed two sets of methods, pooled t-test and confidence interval, and non-pooled t-test and confidence interval. Which one should we use in practice? Firstly, we can always apply the non-pooled t-test and the t-interval, even when the population standard deviation are equal. In this case, the pooled procedure and the non-pooled procedure should give us similar results. But as you can see, the pooled procedures are simpler and easier to compute. We prefer pooled procedure for its simplicity. If the population standard deviations are not equal, we have no choice and we need to apply the non-pooled procedures. As a summary, if you are reasonably sure that the populations have nearly equal standard deviations, use a pooled t procedure. Otherwise, use a non-pooled t procedure.